Okay, I think we are live. Let's see. Okay, you might hear two of me for a second. Okay, you might hear two of me for a second. Okay, cool. Okay. Okay, so we are working on a sort of Vulkan game slash engine right now. Not really sure where it's going. So I did a stream a few days ago where I basically just wrote an initial Vulkan application. I also did a little work off stream where I created a shader tool because we'll need to be doing that. It's a little bit of boring, tedious work, and so is Vulkan arguably, but the shader tool is really like a necessary prerequisite to getting a working Vulkan application, because we'll be writing our shaders in GLSL, which is a high-level language, sort of similar to C++ and Java. But Vulkan doesn't take in GLSL source code. It takes in an intermediate representation called SPIR-V. And we don't do that translation ourselves, obviously. We use a compiler. And there's a standardized toolchain for that already that exists that's called GLSlang. Now that's great and all. You can use a command line tool to precompile your shaders if you're okay with doing that. However, I like a little bit more automation. So I went ahead and I created a tool that I called ShaderSmith. And essentially what this tool does is it lets you specify all of your shaders up front that you sort of want to be compiled into SPIR-V. And you do that through this JSON file, right? So you have this sort of shaders.json file. And here I have a few test cases. This is really just to test it. These aren't any actual shaders that you would use. These are just shaders that I'm using to test this tool, right? And so in this JSON file, you'll notice I have two sections here right now. I have a shader section, and then I have an Uber shader section, right? And to sort of explain why there's like a difference between those two, is that if you're familiar with anything about shader authoring, you know that sometimes there are cases where you might want different variations of the same shader, right? Sort of like in C++, you might want to have macros, right? That sort of control which parts of your code are actually compiled in, right? And you can define that. It might be different for certain platforms, right? Well, in shaders, we want the same thing. We want to be able to conditionally strip out sections of code. And that's mostly for performance reasons and like flexibility reasons, right? We want to use the same shader potentially to do a bunch of different things. Because we don't want to have to write a different shader for every single little thing we want to do, but also it's for performance reasons, right? If we don't need to read a texture for a particular permutation of shader, we shouldn't do that, right? And so that's what an Uber shader is it's like a set of things that a shader takes in, right? Like macro variable values, and it takes all those and it spits out a new shader with those bits of code that is a result of those macros, right? And this is very useful because we can use this to create many different permutations of the same shader, right? But that's not necessarily, you don't need that for every single shader, right? you might not need every shader to support this Uber system. And so that's why we have this regular shaders here as well, is if you don't need to specify any of these Uber variables, you can just specify the shader right here, right? And what happens is the shader is sort of taken, right? Let's go to where the shaders are. The shader is taken in its GLSL form, just like this. And then it gets compiled into an output directory, and it respects the directory structure that was in place from the original source directory, right? So you have this shaders directory that you can structure however you want, and then you have your shaders JSON file at the very root level of that directory that specifies all the shaders you need, and it outputs their binary versions in the same directory structure. And this JSON file is expected to be in the root. And these shaders can also include other shaders, just like you can in C++ code. So that's sort of a rundown of the work that I did. And it's a tool right now that I have on GitHub. And I haven't really decided what I want to do with it yet, whether I want to open source it or not. But that's basically how it works. And so we'll be using that tool in our development of this like Vulkan engine / game thing that we're working on. Yeah, I didn't really do too much work on the Vulkan side of things off screen, but this definitely. I have not hooked this up yet to the Project Vortex yet, which is what I'm calling the Vulkan engine / game thing. So yeah, let's see, what are we going to start on? So let's say if I open the project, I guess I'll have it in another thing, because we might do work on two of these things at the same time. We'll see. Okay, so let's open up the other project too. Okay. All right. So I think the only thing I did, maybe off screen, is I split things out into a different graphics file. So if we take a look at the structure here, we have our main class right here, and this is where we're initializing our GLFW window. And this is also where we are calling into these different Vulkan functions, right? If you'll recall, the first thing we had to do is we had to sort of create this Vulkan instance. We had to set up our debug messenger, specify our extensions that we wanted for this instance, and our layers, right? We also had to check to make sure that these layers were supported before we actually sent them to the instance creation routine. And then we specify our application info, which consists of our engine version, our application version, which API version of Vulkan that we're using, and our application name and engine name, of course. Since we're not using an engine, our application name and engine name are the same thing right now. But that doesn't have to be the case. That's the cool thing about this right here. And I guess the reason these are present is there might be some sort of game-specific or engine-specific optimization that exists out there, right? Like maybe if you're a big engine, like Unreal or Unity, you get that kind of benefit. Okay, so this is our instance creation routine. And then lastly, we are getting this debug function pointer, right? Which is creating the actual debug utils messenger. And this is going to call into our callback right here. Anytime the Vulkan API or validation layer wants to give us some logging information, right? And here, you know, we can filter out if we want to log errors, warnings, information, or verbose. We also added a macro or a boolean here, constant compile time boolean, that can turn on and off whether we do verbose logging. And then we also did our physical device picking here, which is basically just iterating through all physical devices and selecting which one we want. And then we're creating a device, logical device for that physical device. And that is essentially where we ended last time. That took a little bit. So yeah, and so we'll sort of start up there. So we sort of have our connection to the Vulkan API here. But now we need to actually start doing some things with the API, right? So there's a few things we can do. We can start working on the swap chain, which is sort of our backing buffer for the window that we're rendering to. And that might be what we do next. And let's see, if create device, yeah. So we're probably gonna do that. Okay, so in Vulkan, you actually have to create what's called a swap chain, but you also have to create what's called a surface. And the surface is just another abstraction over the operating backing, right, of the window that you're rendering to. So let's go ahead and do that. Let's start with creating a surface here, all right? So we're gonna sort of follow the paradigm that we've been doing with all our other functions. We return a Boolean variable here. We're going to do create surface, and then we'll return the surface like such. Oops. Oh, and here's another thing I did change the naming convention in the other project to use a uppercase. I guess here I'm using lowercase though, so we'll just go with lowercase. And this needs to be KHR, since technically surfaces are an extension, even though pretty much every application out there is using surfaces. It is considered an extension because when you're rendering with Vulkan, you don't have to, render to a surface. You can do off-screen rendering too. Okay. So to create a surface, this is actually operating system specific, and so GLFW provides a function for this. It's GLFW create window surface here, right? So it needs an instance, so we got to take in the instance here. Here, I'll do instance like that. All right, it's going to take in the instance, and then it's going to take in the GLFW window as well. And then the allocation, which of course we're not using the allocator. If you recall from Vulkan, an allocator is just how it gives you the ability to control how memory is allocated on the CPU side, right? And then the output surface here. So we're just going to pass in the pointer to the output surface. And this, of course, is going to return the VK result. And we're probably going to create a macro here to handle this, because as you can tell, like this gets very repetitive. Oh, yeah, returns VK result, right? And we're checking this error code right here. So we'll probably create a macro for that. But if this is not equal to VK success, then right here we could just return false because it failed, right? Otherwise we could return true. Yeah, and so I think that's pretty much all we have to do for this. So we don't even have to do this. We could just return this is equal to success. Like this is just a one-liner operation to create a surface. It's pretty simple. And we should also have a corresponding destroy, because you do have to manually free this memory yourself. And then you really just need to pass in the surface like this. And this doesn't need to be a reference. And then you can do VK destroy surface, KHR. Yeah. Oh, and you need an instance, VK instance, and we're going to pass in the instance like that, and the surface, and null. Cool. So now the create surface and destroy surface routines are pretty simple. And let's go into our main code, and now let's actually do this. So we're going to have a VK surface, and then let's say this is the surface. KHR. If not, create surface. And this is vortex create. And then, of course, we have to also pre-declare these in the header file, right? So let's do that. And let's also pre-declare or do this. So this is going to be struct glfw window, right? Prototype it, whatever you want to call it, pretty clear. So we don't have to actually include it. Here's a general rule of thumb. I don't like including files in the header unless it's absolutely necessary. So that's what we're going to go with right there. All right, so create the surface. Let's go ahead and actually finish calling this function. So this is the instance, and let's rename this instance, and then the window, and then the surface. So it's not, we're going to return 1, and then we're going to log that we failed to create the surface. One thing you may notice is that, like, if one of these functions fails at the beginning of the program initialization, we're going to be technically creating a memory leak, right? Because up here, if we initialize Vulkan, we created a Vulkan instance, and then down here, say the surface creation fails, it's going to fall through. And while yes, technically it is leaking memory, since the application will immediately fail after that, it will be automatically freed anyways. So you could go ahead and do that, but we're not going to really bother with that right here. Okay, and that's just so you know. All right, so we did that, created the surface, and then afterwards, you know, destroy VK resources. Okay, so I'm calling this VK destroy device, VK destroy instance here. And then we're going to call destroy surface here. Yeah. And let's pass in the surface. Yeah. Cool. Okay. Let's run it and let's see if that works. Okay. And let's step through. And no crash, so that's good. That typically means it worked. And remember, we do have all of our logging happening right here. Now, we are just logging right now with the standard output, which isn't the best way to do logging. We will probably address that soon. We'll probably use a library like SPD log or something, but for now, this is fine. Okay. Now, after we have created the surface, we are going to do, I think we can do the swap chain creation afterwards. Yeah. I think we can do swap chain creation at this point. Okay. Yeah, so let's do that. Yeah. So for creating a swap chain, we're going to follow the same pattern. We'll create swap chain. So instance. We also need to pass in the surface. So for creating a swap chain here, vk create swap chain khr. It's a little bit interesting. Actually, this is a device that will be, not an instance. So we need the swap chain create info. Vk swap chain create info. Yeah. Swap create. Okay, that took a lot longer than it should have. Okay, so we have the type, and then there's a bunch of different parameters that we can use here. So we're just gonna, what I like doing is I like just sort of copying the struct when we're filling it up and paste it above and then comment it like this so that we can just sort of reference it as we're filling it up. Okay, so one of the things we need is we need the surface. That's easy. We've already passed that in. Okay. And then we need the min image count. So the min image count can sort of, it specifies how many swap chain images are going to be created, right? So sort of the swap chain is this thing where you can render to one image, but maybe another image is being presented by the operating system. So you can have multiple frames in flight, sort of, right? And it's this trade-off between latency and sort of performance, right? In the sense that, you know, you can have a bunch of frames in flight, but the more frames in flight you have, the longer it is between when you're rendering and when that image is presented to the screen. So you sort of want to balance that. So usually like somewhere between 2 and 3 is a good choice. I like sticking with 3 for real-time applications. So we are going to do that, and that's going to be an option that we do up here. So let's do that. Okay. And then we also need image format. So for image format, this isn't really that simple because we can't just say, hey, I want to use this format, right? Because the reality is that every operating system, every implementation of Vulkan might have different formats available, right? And so we can't just bet on the same format being available every single time, right? It might be on most, but not necessarily on all. And so we sort of have to query which ones are available. Okay. Yeah. So one thing here is that we do have to query some of these things. It's like I mentioned. So let's start doing that up here. Let's see. So we can query what the surface capabilities are of this particular surface, right, that we've passed in. And so let's do that. So let's do vk get physical device surface capabilities, khr, right? And so we need a physical device for this, so we do have to pass that in here. vk physical device, so pass that in. And then this goes in here. It's the physical device that we chose. And then we need the surface that we're using here. And then the actual vk surface capabilities. And then we're just going to call this surface caps, right, for surface capabilities. And we're going to pass that pointer in. Yep. And we also, this can return failure code, right? So if this is not equal to vk success, then we're going to return false, right? All right. So this is the surface capabilities, and we can sort of look and see what's inside here. So let's go ahead and copy this, and let's paste it sort of like we did for this to reference what the struct does, right here. And then let me go ahead and take this and move this up a little bit so we can see it a little bit better. Okay. Okay, so you'll notice in the surface capabilities that there's actually a min image count and a max image count here. And what that is that could affect this number right here. So what I want to do instead of passing this in is we're going to sort of pick a number, right, in between the min image count and the max image count. And so, yeah, so this min image count could be, 1, it could be 2, right? But we sort of want to have a preference here, right? So let's say we'll have a variable here, const expr, let's say it's a UN32, we'll say it's a preferred image count, right? And let's set that to like 3, right? But our actual image count is going to be a result of clamping, right? Or I guess we could just put a direct link here, right? Let's do standard clamp. I guess that's not a thing. We're going to take, I thought that was a function in the standard library, standard clamp, C++. It is, yes, it's just in the algorithm header. So let's go ahead and include the algorithm header. Okay, and yeah, so standard clamp, and then we're going to clamp this preferred image count to be in between the min image count and the max image count, just like such. There we go. Yeah. All right. So now, our swap chain also needs a format. So let's see what formats are available. So to get the formats that are supported here, we call another function. It's called vk-get physical device surface formats khr. Yeah, pass in the physical device surface, and then we have to get the count first. So the surface format count. We'll pass that in, and no pointer. So this is going to get the number of formats, and then we can actually put it into a vector. So vk surface format khr surface formats, and it's going to be initialized with surface format count. And the next time we call it, it'll actually populate this data vector. Now let's put this in a block here. Okay. All right, so now we have these surface formats. And a surface format is a combination between an actual VK format and a color space, right? So the format is going to be the actual packing in the buffer, right? So think of like RGBA8, or think of HDR formats like 16-bit or 10-bit, right? These are all different formats. Also think, it could be sRGB. That means that when you write to the frame buffer, you're going to have a hardware transfer operation applied to your color data, right? So if you're doing all of your shading in linear space and you're writing to an sRGB frame buffer, that data sort of needs to be transformed. It's called an EOTF, electro-optical transfer function, to be in the sort of correct gamma space, right? And that's all done for you. And typically we do want to use an sRGB buffer. So, and then color space is just going to be how it's interpreting that data in that frame buffer, right? And so sRGB is one, and there's a bunch of other ones, right? Typically we care about sRGB nonlinear because that's primarily what most monitors are going to be using. So we're going to be doing that, or those are the ones we prioritize. And I think the Vulkan spec actually requires that a certain combination of these exists. And I believe that is a BGRA8 and the sRGB color space, nonlinear. I believe that is a requirement for the spec to support. So if that's the case, we're going to use that. But let me see. Let me look at the spec real quick. Let's see. Vulkan K surface format KHR. got a little bit of a freeze here in the spec. Okay. So I think that, I'm pretty sure though that it is. We'll look through the formats that are supported, but I'm pretty sure it's BGRA8. Okay, so we're going to do this. So if we get the formats here, and then we're going to go through each format, right? Going to go through these formats, just like that. Okay, but then we also need a rank, right? So let's go ahead and do this ranking. So we're going to have a map. Okay, and this is, okay. Let's say, yeah, it's gonna be a tuple. We'll just do it all here. We want a VK format, and then we also want a format. Here. Or we could do this, so we're just going to create a function here. Let's get surface format rank. So this function is just going to essentially return what our ranking is, right, for this format. So let's say format dot surface format. BAGAR8. Ignore him. And the color space is equal to nonlinear, then let's return 1. Otherwise, we're going to return 0. And this is basically just going to prioritize this format combination, right? Okay, and then, okay, and then UN32 rank equals get surface format rank. And then we're also going to have a format. Let's put this up here. Chosen format rank. And then let's assign this to 0. Sure. The higher the better. If rank is greater than chosen rank. Rank, and then we'll do the chosen format. This is surface format. Okay, so this is just going to pick our most preferred surface format. So we're going to take this format and in our swap create, the format is going to be equal to this chosen format right here. Is this VK format? Yeah, this is VK format. So this is dot format, and then the color space. It's going to be the chosen format dot color space. Might not be initialized. Okay, and then we'll just do a default initialization. Yeah. Cool. So that's the color space. And the format. And let's actually initialize this as an N32, and let's make it, right now, we can keep it like this, but if we go to there, we're going to return 1 for everything else and 2 for the format right here, so that when we initialize it to 0, the first format will be selected no matter what, because we'll have at least a score of 1, right? Okay, so that's the format and the color space. Now we need the extent. So this is going to be passed into here. So width and height. Okay. Now, this is where it gets a little interesting about the width and height, because you think, oh yeah, you could just pass the width and height right into create swap chain, right? But actually, if you want to be completely cross-platform, that's not necessarily what you need to do, because this capabilities right here might actually have the extent already specified. And I believe this is the case if you're on like a platform where, maybe I'm wrong about this, but like say you're on a platform where this is already determined the extent, right? And so you're not, it doesn't really make sense to specify your own extent, like maybe, I don't know, a console or a phone or something, maybe that makes sense. I don't think it makes as much sense on like Windows, where like, you know, you're sort of controlling the size of your window, right? But this is there, and so we need to account for that, right? And so what we're going to do here is we're going to have a swap width and a swap height, right? And then if the current extent, if either of these values is set to something besides like the max uint, right, which is uint32 max. I actually prefer doing standard numeric limits uint32 max because that's a slightly more modern way of getting the maximum value. So if either that one or the height is not set to this, then we have to use this value, right? That's just how it is with the Vulkan API. Right? Otherwise, we can use our own. However, we have to keep it within the limits, right? There's a min and a max too with this, right? Current extent, but there's also a min image extent and a max image extent, right? So we can do this. Besides, we have to clamp it, right? So swap width. We're going to clamp that to surface caps dot min extent dot width and then dot max extent dot width. So we're sort of just capping it right into those extents, and the same thing for the height as well here. Min height. There we go. All right, and then we'll use that swap width and swap height down here when we create the swap chain. So VK extent 2D. We'll just go ahead and do that VK extent swap extent. There we go. Okay. So now we have the swap extent. So we can take that swap extent and use it down here. Cool, so that's the format, the color space, the extent, and the image count. Next, we have to worry about, okay, so image layers, this one's easy. This is just how many, so if you're creating like an array swap chain, right? So like, say if you're in VR, right, you might have 2 swap chain images like that, but we only have 1. So, you know, we're good there. There's nothing too complicated with that. Okay, so image usage. This is another interesting one. This is how you're going to use the swap chain image. And this is interesting with Vulkan because you have to specify upfront what are your intentions with the swap chain. Like, are you going to use it to draw to? Are you going to use it for transfer operations? Are you going to use it to present to the screen? That kind of thing. So actually, you don't have to do one for presentation. That's not a thing. But you can see here, these are the valid usages of an image. So for now, we're just going to do color attachment. This will change in the future because eventually we probably won't render directly to the swap chain image. We'll end up rendering to an off-screen pass, and then it'll get blitted into here. And usually when that happens, the swap chain is a transfer destination and not an actual color attachment. But for now, we'll leave it as color attachment because in the first bit, we are going to render directly to the swap chain. Okay, so image usage, and then image sharing mode. This is another thing that we don't really care too much about. So sharing mode. So this is if you're using multiple queue families in Vulkan, you need to sort of transfer the ownership of the swap chain, right? But since we're not doing that, we can just leave it at exclusive because we know it's only going to be used by one right now. And concurrent and exclusive means it's only going to be used by one at a time. Concurrent means that it can be used by multiple at the same time without any sort of additional synchronization. As far as I'm concerned, however, the performance may be worse. Might need to look that up in the docs. Don't quote me on that. But cool. All right, and then the next is the queue family count. So this is queue family index count. This is, like I was just saying, how many queue families this thing can actually be accessed by, right? So that we now actually need to pass that in here. And this is a bug. This should be the width parameter. Okay, there we go. That would have been a bug right there. So we need to actually use the parameters there. So now we need the graphics present queue family, right? Or I should say, yeah, this is the queue family index, right? So we're telling it that we're going to be using only one queue family for the swap chain, and it has to be an array, right? Queue families, right? So we're using this one, right? And let's actually do standard size of that, and then we're gonna do .queue families equals queue families. So we're telling it which queue families are actually using the swap chain. Cool. All right, and then pre-transform for the swap chain, we don't care about this, so we're gonna leave it at the identity. I've never used this, to be honest, but I think that it just lets you do rotations and mirrors, right? And so that's sort of like a faster way to do that kind of thing, but we don't need to do that. So we're gonna set that to identity. Nope, not inherit, identity. Or maybe we do want inherit. I think we want identity though. We want the current transform. Okay, that's interesting. Yeah, so we want whatever is in the surface capabilities, right? So whatever is in here, we want the transform, right? So we don't want to modify that. Yeah, and I guess that's operating system specific there. Okay, so we get the pre-transform, and then composite alpha. So this composite alpha is like if you want your window to be transparent. We do not want our window to be transparent, so it's going to be set to opaque. And you could probably do some pretty cool stuff with that, but I'll leave that to the viewer to explore. Okay. Present mode. All right. So this is another thing where we're going to need to do a little bit of work on. As you can see, Vulkan is all about doing work, right? This one's a little bit simpler than the format and color space though. Whereas we had to go through all of the available formats and choose the one that we wanted right here, the present mode is simpler in the fact that we only have one thing that we need to choose from, not like a combination of two things, right? And so choose present mode. So we're going to pk get physical device present, surface present modes, physical device surface present mode count. And then if this is not equal to success, we actually need to do that right here too. Okay. Then we're going to call it again, but this time we're going to have a vector of vk present mode kchar, present modes, initialize with present mode count, and then pass up the data here. Okay, so now present modes, there's not very many, right? There's immediate, there's mailbox, FIFO, FIFO relaxed, and each of these has their own thing. Immediate is just, it's not going to wait for anything. It's just going to immediately, essentially, as it sounds like, as soon as you present the image, right? And presenting an image, just so you know, it's when you're done rendering the image and you're ready to give it to the display engine, right? To actually present to the user on the monitor. And this is where things like VSync and, different methods of handling that come in, right? We want VSync. We don't want to be rendering more frames than the monitor can handle. That's kind of silly. And so what we're going to use is something called mailbox. And mailbox is where I think we want to use mailbox. Let me make sure. Mailbox is where there's like the last one is overridden. So maybe, okay, so mailbox specifies the presentation engine waits for the next vertical blanking period to update the current image. So yes, this will VSync. Tearing cannot be observed. An internal single entry queue is used to hold presentation requests, right? So this is basically VSync right here. And this immediate right here is essentially not VSync. And then FIFO is not the exact same as mailbox in the sense that this does wait for VSync. However, this uses a different queuing mechanism for the frames, right? Yeah. So I think the one we want is the mailbox KHR. Oh, actually, we might want FIFO because it says this is the only value of present mode that is required to be supported. And it's nicer if we don't have to actually look through all of them. Yeah, we might just use this one since it's not actually, well, it is required to be supported. And this is exactly what we want because it does do VSync. Used to hold the present. So append it to the end of the queue. Yeah. Yeah, so we're going to just go ahead and set this to FIFO because it's we don't really need to do anything other than VSync. So let's just, if we need to ever consider other present modes, we'll do that, but we don't. So this is nice and simple. Cool. Okay, so that handles the present mode. And now there's this clipped thing, which I think for clipped, it's basically just if a pixel is not visible, like obscured by another window, then it's going to sort of allow the operating system to discard that pixel. And maybe if you're doing something where you like care about those pixels still, you'll set this to false, but we don't necessarily care about those, you know, maybe for performance reasons or whatever, but yeah, we don't care about that. So we can just set that to true, that those can be clipped. And then there's also the last parameter is the old swap chain. And I guess this can sort of optimize the creation process of swap chains. And maybe we'll try to use that, but for now we'll leave that to null handle. And I think that's everything for swap chains here. Yeah. So now we can actually just pass this swap create into the vk create swap chain. And then, yeah, here we'll do swap chain kchar, out swap, and this will be a reference. And then down here, we can just go ahead and pass this in. And then this returns if it's equal to vk success. Yeah. Cool. All right, and then we can delete these since we're done referencing. All right, and then, yeah, now I think we're ready to test this here. So let's try to create our swap chain. Physical device, logical device, the surface, the width, yeah, so the use 800 by 600. And then the graphics, graphics percent Q family, and then the output swap chain. Failed to create Vulkan swap chain. Cool. All right, let's test this out. Surface capabilities. Okay, so remember how I was talking about the current extent? So I guess the current extent is still filled out in the case of Windows, which is interesting. And I guess it makes sense, right? It doesn't really matter what width and height we passed in because the surface sort of already has a width and height, right? So I'm not, this is one of the weird parts of the Vulkan API where it's kind of like, you know, why would we pass in the width and height if it's just going to be overridden anyways, right, by whatever's in the surface capabilities. So, you know, it is what it is, but that's just to handle platform differences. And I have hexadecimal display turned on right now. Okay, so that 800 by 600. And let's go and see what surface format produces. Okay, so notice how, yeah, there's 4 surface formats supported here. So I have, all of them are sRGB nonlinear. So there's RGBA8, but there's also BGRA8, UNorm, and sRGB, right? And so it's going to find our preferred format here, and our preferred format comes out as the BGRA8 and the sRGB nonlinear. So that looks like it works correctly. And then we come down here and we create, and we end up with it not working. And it says create swap chain. Driver's function pointer was null. Returning VK success was the BKKHR swap chain extension enabled. So it's probably going to be a device extension that we need to use here. Yeah, it's probably that we haven't enabled some sort of device extension. So let's see, let's create a logical device here. Okay. Is there a function that we need to call from jailbreak to get required? We need VKKHR swap chain. This is a device extension, okay. Yeah. So we just haven't specified that device extension. Okay, so let's go to here, and we need to actually put our extensions here. So, put extensions, yeah. So this is a vector of card pointer extensions. So required extensions, we absolutely require the swap chain extension. So KHR swap chain extension name. And that extension count is going to be here. And extensions.data. Cool. So let's see if that works. All right, did not get an error that time, so it looks like that did work out. Cool. All right, so that is creating the swap chains. And so now let's go ahead and submit that. Create Vulkan swap chains. Yeah, there we go. Okay. All right, so we have that swap chain created. Now, once we have the swap chain created, we got to actually do something with the swap chain, right? So if you recall, so we have images that the swap chain sort of has, right? And we didn't create those images. Those are sort of owned by the swap chain, right? And we can't render directly into those images without something called an image view. And an image view is sort of just like a sub-resource. It's like a view without being circular, right? It describes a sub-resource range into an image, right? So you can imagine if you have like an array image, it could have like a base layer, a number of layers. Maybe it's just the red channel, maybe it's just a combination of channels, right? So you can describe like a range of resource or sub-resources within a resource. And so we sort of need to do that for the swap chain, right? So we're going to do that. We're going to create a function called create swap chain images. Swap chain. That out. This is the reference here. Okay, so first we need to actually get the images of the swap chain, right? And so there's a function for that. Obviously, vk gets swap chain images. So we need the device. Swap chain image count. Okay, and now I'm about ready to make a macro because of how many times we're repeating ourselves. So we're going to make a macro up here. And it's going to be called, let's just say, check vk, right? It's going to take in a Vulkan call. And we're just going to simply say if vk call is not equal to vk success, return false. And everywhere we're we're doing that pattern, we're going to do it. Right, so like right here, for example, check vk. Okay. All right, now we can say vk image, swap images. Okay, we have the images. Now we need to create a view for each of them. Now we need to create an image view, and that takes in a few parameters. So let's see, what does that take? So it takes in the sub-resource specifications here. Do we need any flags? Does not look like it. No, we'll leave that at 0 for now. Image. just do that directly. And then we need a view type, so this is going to be 2D image for the swap chain case here. And then we need the format. Format is just going to be whatever format the swap chain is. Yeah, so we're going to need to pass that in. And then components, this is like Swizzle, like if you want to exchange, RG components or whatnot, but we don't need that. So we'll go with that. And then we also need to specify the sub-resource. So this is like if you're going to use the color versus the depth buffer. If you want to have multiple layers, and then also MIPS. We only have one MIP. So. I think that's everything for the sub-resource range. Yeah. And then we can do GPK. Function can go into our header. Oh, it already is. Okay. So now our create swap chain should probably return a little bit more information here. I mean, like the format and whatnot. So swap chain result. Let's do this. So it's going to contain the actual VK swap chain. Or maybe I should just say swap chain. Yeah. Swap chain, and then BK format. And then also the extent. Cool. And we're just going to return this whole swap chain as a result of this create swap chain. Present mode is always going to be FIFO. Put these directly into that struct and use them later on. And then here we're going to do result swap.m format surface format. So I'm just going to forward all that data here. And then when I return it, BK right here. And then we're going to do out swap equals result swap, and then we're going to return true. Just like that. Cool. Now we have all that extra data that we can take advantage of over here. Make sure that still works. All right, cool. That looks like that still works. And we get the format, color, space, extent, and present mode that was chosen to go along with it. So now let's call into our thing here. So we're going to have BK image view, so swap image views. And I'm tempted to just put these directly into here. Yeah, let's just do that, because these are going to always be used with the swap chain, right? So, image views, we're just going to go straight into here. Yeah. Probably should also create a macro for some of these. All right, looks like that worked. And we have our image views. Yes, as you can see, there's 3 images. Yeah. So our preferred image count is 3. Yep. Okay, let's go ahead and push that. Yeah. All right. I'll get rid of that code right here. All right, and now we need to have code to delete these. So let's have a destroy function. Yeah, let's do void destroy swap chain. Yeah, and so this is going to clean up the swap chain and the images. chain swap. Unresolved symbol. Let's see. Oh yeah. Cool. All right, that should clean up all of our resources. All right. My chair keeps like running over my cord. Okay. So now we have our swap chain image and our image views. What can we do? Okay, so now we need our sort of like our frame loop. So this is where we get into like Vulkan synchronization stuff, but we're going to need fences and semaphores. So let's do this. We're gonna have a struct here for a frame, and it's gonna sort of be like a frame in flight, right? And one thing we need is a fence. We also need some semaphores here. So image acquired. So this is gonna wait for an image to be acquired from the swap chain, and then we also need one for when rendering is complete, so we know when to do the actual presentation. And let's have some functions here. We're going to have a create frame and a destroy frame. Okay, so we need to just create a few resources here, like bk create fence, device, and then bk fence create info. And then for this fence, we just need some flags. This one, we actually do care about the flags because we want to start it as signaled. Yeah. And then we can go ahead and create it. So this is also going to be a check. Let's create. And then we also need to create two semaphores. Okay, so the semaphore also has some flags, but we don't care about those. We literally just need to set the type here. And then we can do check bk to bk create semaphore device. create, and then we can just do this twice. We need two of them. And if this all works, we can return true. And then destroy frame is just going to destroy that fence that we created. Of course, it needs the fence. And we also need to destroy those two semaphores. And the amount of frames that we have is dependent on the amount of frames in flight that we want, which can be a relatively constant number, or it will for sure be a constant number here. This can be made reference to const. I'm not actually setting anything here. Cool. Okay. So over here, we're going to have the amount of frames in flight that we want, basically. So frames in flights. So that's all you can see. This is also a good time to have some graphics struct to store all of our graphics related variables. So maybe we can call it like graphics context or graphics information, right? So we need the instance for our Vulkan. We need the debug messenger. And debug messenger. Physical device. All Q, and we need our surface. There's a lot of fields in Vulkan, as you can see, and we aren't even rendering a freaking triangle, baby. Okay, so yeah, surface, swap chain. Yeah, this is pretty good, yeah. So, inside some graphics. And we might as well make a function that is going to destroy graphics context, and one that's going to create graphics context. destroy, we'll just do this. Cool, now this simplifies the main loop a lot. Okay, so now that we have this all split up and cleaned out, this is creating all of our core data that we need for Vulkan. Complaining that our constructors don't initialize, we'll just add braces to all these so that it doesn't complain. Okay, cool. So let's see, make sure that still runs. All right, no issues there. We'll go ahead and commit that. Clean up main file. Consolidate into graphics context. Okay. All right, so we were working on the frames, create frame and destroy frame here. So we have our fence and our semaphore. So the way this works is we need to actually acquire a swap chain image, right? And so let's see if we can, we'll start writing that code here. Yeah, so we need to actually acquire an image. So get results, acquire results. And this device. The swap chain is how long we are willing to actually wait to get this, and we don't care, so we can just do the max. And this is where the semaphores come in. So this is going to signal a semaphore, and this is, so we need our frames here. So let's actually, let's see. Do we want the frames as part of the graphics context or outside of the graphics context? I think we want them out of the graphics context. Yeah. So let's go ahead and create our frames. Maybe we'll create like an application context. And the graphics context will be in here. So the window. And this application context will also have our frames in flight. Be a standard array, frames, and we'll just get rid of that because we can just do it right here. Cut this out. so now we actually need our current frame. So current frame will start at 0, which is the same as just doing that. So let's do that. And then our image acquired semaphore will be passed in right there. And then we also need a fence, right? Do we want a fence right here? I don't think we need to use a fence right here, so we can just pass in vCandle handle. And the image index, this is the index that we're going to get. Yep. So we will put this acquired swap index. I don't really, do we want this as part of a persistent application context? Maybe not. I don't think that's proper. Let's just keep it above the loop. Yeah, current frame. This will be our current frame index. We'll set that to 0 there. And at the end of the loop, we will set it to +1, and we will mod the number of frames in flight, which is going to be an application frames. Or can I just do? Yeah, let's do that. Okay. And that's the selection. Okay, so this is giving us the acquired result. Okay, so we've acquired the image. And this result can actually be a few things, but right now we're just going to assume that it's either a failure or success. So if it's a failure, which means it's not equal to success, we're not even going to handle that, because if that happens, it's either going to be our resize or something catastrophically wrong has happened, right? And those are sort of two separate cases that we'll need to handle. Okay, so I think before this is when we actually need to do our wait operation. So this is where we actually wait for the previous frame to finish, right? So we're going to do this. Or yes, just current frame. And then one fence. Then we have a timeout, and we don't care how long this takes. Okay, and then we want to reset it immediately after. Okay, so that resets the fence, and then we acquire an image here. And then we want to actually present this image. In between, we'll want to do something with the image, but we'll get to that point soon. So acquire image. And then present image. So we need to call ek q present, and this is where we pass in a q. And then okay. So we're gonna wait on one semaphore. And these semaphores that we're waiting on are just the current frame rendering complete semaphores there. So that means this actually has to do something. But since we're not actually using that, we're just going to use the image required semaphore, because otherwise the rendering complete semaphores will never actually be signaled. Okay, and then we also need to say which swap chains we're going to be using. That's just going to be graphics swap. The image that we want to present is going to be this acquired swap index right here. And then there's this results for each one. I'm not actually sure what each one of those stores. Maybe it's just an individual result. Present info. Do not need per swap chain results. Can use null for periods of non-null. Each enters the result. Oh, okay. Yeah, so that's if you need per swap chain results, but we don't care about that. Okay. So ignore that for now. Let's see how this. Okay, so we wait for the fence. Validation error, let's see. Wait for fences. Required parameter. Fences specified as null handle. Okay. So that means this fence wasn't actually created because we didn't actually create the frames yet. So let's create frames here. We need to create the frame is less than. Is there not like a static way to get the size? Probably not. Okay, so there is a way to do this. It's tuple size. Okay, frame 0. And then frame 1. Alright, cool. Waits and then it resets. If you get a validation error from that. No, we did not. Cool. So then we acquire an image. Worked well, the acquired result is 0, and then we present this image. Validation error. Present images past 2% must be in the image layout present source or shared. Okay, so this is where we actually do have to do some layout transitions to get the layout in the right format for presentation. So this is pretty cool. Let's see. So I'll make a function here. Let's make a function so that we can immediately submit a command buffer. We'll call it immediate device. Okay, so since we're sort of getting into command submission and stuff here, I'm gonna submit this code. It's not fully functional because it does technically need the layout transition. Create frames image. Okay. So So we need a command pool. Let's create the command pool. Create command pool. Type. Then let's see, what flags do we need? Transient reset command. Okay, so this transient bit is kind of interesting because it means that the command buffers allocated within a command pool will be short-lived, which is pretty much what we want for at least this initial command pool. And then this reset command buffer bit. Okay, so let's just pass these flags in. So we're going to have a transient command pool. As part of the graphics context. And transient command pool. Okay, I'll be right back. Okay, and we are back. So earlier we were creating the transient command pool for our temporary command buffers. So we created this transient command buffer, but now we actually need to do our image layout transitions here. Okay. I don't know why that's giving me the red squigglies, but let's create our immediate function here. Okay, so let's do immediate, and this is going to take an device, and it's also going to take in a command pool. And then it's also going to take in a function that returns nothing but takes in a BK command buffer. Okay, so what we're going to do is we're going to do allocate command buffers. Command buffer allocate info, command allocate. I just want one. These are going to be primary command buffers. Yeah. secondary command buffers, or command buffers that can sort of be embedded into other command buffers, but we don't need those right now. They'll be useful when we get to multi-threading. Okay, and then this is going to return our command buffers. We need to do a check K on that. And let's make another macro that is not going to return a boolean, but it will do a void return here, since we're not planning on returning anything from this function. Yeah. Okay, and we also need a fence. So we need to create a transient fence here, temp fence, because this is going to immediately execute. I guess we could do this without creating a fence and waiting for it to complete. Yeah, I think it's just the command buffer part, because we can always externally synchronize these things. Yeah, so we have our command buffer, but now we need to call the callback on this command buffer. Oh wait, but the problem with doing that is then that the command buffer needs to be deleted, but in order for it to be deleted, we have to ensure the work is done on the GPU. So, correction, we do need a temp fence here. And then I'm just gonna take this right here, and let's go ahead and make a helper function here. Okay. Yeah, let's do create fence. This may be useful for other things too, so let's go ahead and put it here. Fence. We can call the rendering functions, and then we need to do a submit right here. So it needs to go into a queue, and we also need a submit info. Okay, so I don't think we need any, we don't need any semaphores. Yeah, we don't need a signal or wait on any semaphores. Yeah, but we do need a command buffer. Here's info.command buffer. Command buffers. And this is going to be equal to our command buffer. And then when we actually go to submit it, we give it this temp fence up here. Oops. And then we can wait on the fence right here. And let's actually pass in the flags right here. we don't want to create this fence signaled here, but we do want to create other fences signaled. Yeah, so let's right here. Fence device, and we want this signaled. Okay. Now we can wait on this fence, wait for fences, and temp fence, and wait all, and then call this submit and wait. Create temp resources. And then we're going to do free temp resources here, which we just need to destroy. Fence. That's going to be our temp fence. And we also need to destroy our, or free our temporary command buffer here. We'll call this also temp command buffer. We need to free it right there. Cool. Now, yeah, that's pretty much it for our temp function here, or our immediate function, I should say. I just need to update the definition. Cool. Create defense, and this one too also takes in flags now. Okay. All right. Okay. All right, and then I want to make a nice function for transitioning an image layout. So let's now start getting into commands, right? So commands. So we do what's called an image barrier. So we do need a command buffer. And then we need an image. I think I'm actually going to make this a struct. Well, actually, it's pretty much already a struct. So let's see. This is really just an ergonomic thing. So let's go over here where we create our swap chain, and let's transition swap chain here using our new immediates. So we need the device. Transient command pool, and using this command buffer. Okay. So now we can do VK image barrier, or VK pipeline barrier. Okay. So command pipeline stage flags. So yeah, I think I do want to put this into a struct. Stage top of pipe, because I don't really necessarily care about all this for some things. So top of pipe, so let's dependency flags. Dependency by region, I think. No memory barriers. No buffer barriers. What does pipeline barrier 2 look like? Okay, VK dependency info. This one might be a better function. Image barrier. So these are not initialized by default since this is the C API, so I will need to make a struct for this to be compatible with C++ 20 initializer lists. But for now, we'll do this. So top of pipe, bottom of pipe, desk stage. Okay. VK pipe. Oh, this is VK access none. Don't have any access masks. Okay, VK image layout. So we're going from undefined to present source. Source family. Is ignored. Yep. Family ignored. Because we're not doing a transfer here. And then the actual image. Let's see. So we have our swap chain images. Are those persistent right now? So we have image views, but we don't have the images as persistent, so probably should do that as well. Yeah. Let's actually get the images when we create the swap chain. Results, images. Okay. So these two. I'm going to pass in the image count now too. Actually, no, I don't need to pass in the image count. I need to pass in the actual swap images. Yeah. Okay. Now for the image, I can do graphics.swap.images. I can do the 3 of these. Yeah, and we're gonna do this. Swap.images. We need to capture that too. So we'll capture that by value actually, because we don't need to modify it. Okay. So now what we can do is this image. Swap. And then we can do images, and sub-resource range. Designated initialization here. Okay. Aspect mask is aspect mask color 0 to 1, 0 to 1. Definitely creating a function for this right here. And then we can do image barriers. Image equals that. pass in our command buffer and pass in the dependency info. Cool. All right, let's see if this works. Fail to create endpoint frame at index 0. For our VK macro, let's also do, let's do this. It's helpful if we actually know what error was output. There was an error, right? So let's do I don't want to pollute the scope here. Actually, I can create a little temp scope here. And this works. this just needs to be not. So that was probably why it wasn't working before. Cool. So we got past that part. Let's see. Now we have our image transitions. Let's see how this goes. Get an error. Pipeline barrier. Dependency flags is 1. Barrier count, image barrier count is 3. 0, 0, next. Command pipeline barrier 2. Is this like an extension or something? Or just the Vulkan version? Sync to, oh, it's part of Vulkan 1.3. Or if you have the synchronization 2 extension. Might need to enable that extension. See how many devices support it first. Every time this happens on Vulkan GPU info, where the extensions don't load the first time, it's like, what the heck? Okay, sync to 38.32. Huh. I thought more would have supported it by now. I guess we'll just stick to the first one that I don't like. Probably just emulate that function. Validation error. Type must be, oh. Okay, yeah, I didn't set the type right. You must call begin command buffer. Okay, cool. So that's pretty easy. In our immediate, we just have to call begin command buffer. This is our temp command buffer. Command buffer begin. One time submit. We do want that. And that's it. And command begin. And then we want to end the command. Temp command buffer. And these can all return codes, so we'll just grab them. Okay. Boom. All right, so that works. No errors. Cool. All right, and we're getting spammed, so what does it say? Present images must be in layout, present source, or shared, but is in undefined. Okay. So it doesn't actually think we transitioned them. Okay, so it happens on the second image. Ah, I think I know why. Yeah. Gotta pass in the size. Because we're only doing the first one right there. Cool. Okay, now it's just a black screen. To step over the white screen, because now it's actually acquiring and presenting images. Let's go ahead and submit that. Immediate submit function. Image barriers for swatching images. Okay. I want to make a function for this because I don't, this is not very ergonomic. But maybe once we have a few more of those, we will do that. Yeah, actually, let's do this. Okay. Let's do... Yeah, let's do rendering to the swap chain. Yeah. I think I'm gonna do the GUI integration so that we can have GUI, debug GUI. So let's go ahead and fetch that real quick. Okay. Let's get GUI here. So GUI is this nice debug library for UI. It essentially embeds the UI into your command buffers directly. It's quite nice. Why not include Live Godot? Well, maybe I will one day. We're making everything from scratch here, though. Let's see. Okay, so we're gonna take, so we have this library here. We added it to our dependencies list. So let's go ahead and start integrating this library for the GUI. Okay, so we're gonna do this. Let's include it here. GUI. I'm GUI. Start reconfiguring. Oh, that's right. I'm GUI library is not actually a CMake target. Forgot about that. So we have to sort of add it ourselves. Okay, so let's add I'm GUI. We can add it directly to our sources, but I'm going to add like a little library here. So let's do add library. It's going to be called GUI, and then it's going to be an interface, which means it's basically just, well, actually no, it's going to be a static library. Yeah. Okay, so, and I think we want GUI. I have to look up how to do this in CMake. We have to make our own target, so let's see. Yeah, okay. So it's going to be the source directory. And then we're going to take imgui.h. Actually, I think that symbol goes before, yeah. And imgui.cpp. Let's see, does that work? Okay, no, it's error here. Cannot find source files, imgui.h. See if it actually downloaded correctly. And we're going to build dependencies. And here it is. So the source file is right there. Maybe it should be lowercase. Yes, it has to be lowercase. Very weird quirk, but okay. So we need that, and we need the internal. I'm doing internal.h, and take the demo.cpp and draw.cpp tables and widgets. I think that might be it. And then we also need the backend for the one that we care about, which is going to be Vulkan and GLFW. Yeah. So I'm GUI impl vulkan.cpp, and we also need the .h file here. And then we need the two GLFW files. Okay. And now we're linking to it, so that should, oh, I got an error here. Cannot find the impl vulkan.h. Oh, it's yeah, it's backends plural. Okay. Cool. Plural. All right, and now we need the target include directory. Yeah, so we need to define the include directory for this. Include directories of our GUI target. This is public, and this is going to be equal to our root directory here. Let's see if we can include it now. I took it off accident. Okay. Alright, cool. Now we can include it. So include that. Alright, now we need to actually initialize our I'mGUI stuff. So let's do init I'mGUI. And what do we need to do for initializing I'mGUI? So we need to call I'mGUI impl glfw. We also have to include our backend here. So say I'mGUI, and then let's include backends impl Vulkan.h. Yep. And then also glfw. GLFW and init for Vulkan. And then we need the window, GLFW window. And install callbacks. Yes, we do want that. And then we now need to initialize the Vulkan aspect. So Vulkan GUI Vulkan init. So and we need to pass in our graphics context. So it needs our instance. It needs the physical device we chose. It needs the logical device we've created. The queue family that we're using. The actual queue that we created, so the all queue. And then it needs pipeline cache. We're not actually using that, so we can actually just set that to the null pointer. Oh, and this is something we don't have yet, but we need to create a descriptor pool. So we're going to have a to-do that here. Yeah. And then we need a allocator, which is we're not using, so null for that. And then the min image count. This is just we'll just set this to the number of images that we have in our swap chain. This is a uint32, so we should do a C++ cast here. And then check Vulkan result function. So this is for callbacks, and we're not going to actually use this right now. And then lastly is the MSAA sample, which we're not doing MSAA, so we could just leave this at 1. And then we actually call the impl Vulkan init. And we pass this GUI Vulkan init. And we can return this. And then we have to, this is where our immediate function comes in handy here. So we have to upload the fonts to the graphics card that it uses. So using the all queue and the transient command pool that we created, we are going to, I always forget the VK prefix. We're going to upload these fonts, right? So we need to do I'mGUI impl Vulkan create fonts texture. And that just takes in at least I thought it took something in. Does this not do that anymore? I guess we can just call this function straight up now. Used to have to pass in a command buffer into there, but it looks like it does that on its own. Yeah. All right. And then we're going to call this right after we initialize our graphics context. Context.window, and then the graphics. Failing to include Vulkan. Ah, yes, it needs to be linked against the Vulkan target as well. So we need to link the I'm GUI against the Vulkan headers. All right, and those red squigglies go away. Now it also needs to be linked against GLFW, so let's do that as well. GLFW. All right, and we've created. Cool, and of course we get an error because we forgot to do the ImGUI initialization itself, right? So that is initializing the backend, which we will place all of this into a block here. Initialize ImGUI backend, but we also need to initialize ImGUI itself. So first thing we do is we need to check the version and make sure that the version is correct. Checks that it's matched between the compiled and the caller. This is just something that is recommended to use. And then we can go ahead and create the context. Now we can pass in the flags. And do we want, okay, we don't have access to that. So what we need to do, I want to actually use docking features, which is a different branch. We'll turn those on in a second. We do want to enable some things. I think we might just be able to leave that blank for now. Populate that settings. Okay, then we set the style. Let's set the style to the dark by default. Okay. Yeah, that's pretty much all we need to do for now, right there. Here. All right. All right, yep, and then now descriptor pool is equal to null pointer. And so that's something that we can work on now, is creating the descriptor pool. So let's submit this. Pool and ImGUI like GitHub and initialize context. Says descriptor pool. Yep, and let's also, push that. Okay, so now we also, we need to create our descriptor pool. We also need to destroy, vk destroy command pool. We need to destroy our transient command pool. So let's do that right here. Need to reorder that because we don't want to destroy the swap chain after we destroy the device. Okay, so now we can create our descriptor pool. Let's do create descriptor pool. Okay, and then we need our VK descriptor pool create info. Descriptor create info. Type is equal to descriptor pool create info. Alright, and so we just need to specify a few limits here. We'll create one for I'm GUI, and then we'll also create one for our own uses. We'll keep them separate. Okay, so what flags do we want here? Free descriptor set. I think we want that one. The descriptor sets can return their individual allocations to the pool. Okay, yeah, I think we do want that by default for all of our descriptors sets. And then max sets. Yeah, so let's just go ahead and pass these in. So max sets. Sizes. Okay, and then VK descriptor pool size. Yes. Okay, so we need a vector of these. Yeah. Or at least an array of them. Yeah. And we need to essentially define like how much of each type of descriptor we want to support. So let's see which of these we care about. Sampler, combined image sampler, that sampled image, storage image, textile, yep. We want all these. And the dynamic input attachment, inline uniform block. We'll just, I think we basically want everything up into input attachment, yeah. And then what we can do is we can say, we'll just give ourselves like 1,000 of each, or maybe 10,000. You really don't need to, this is just the maximums that you're allocating of each one. Essentially they're the upper limits, you can always allocate more. full size count. Yeah. All right, and then we allocate this. Disk. Actually, I'm not going to pass that in yet. We're just going to say that's. This is just going to be out pool. Out pool. Okay. And it's going to return a bool. So we're going to do return if this is equal to PK success. All right. Okay, cool. Now we're going to create this descriptor pool right here. Pool. And then we're going to create one for the GUI. Descriptor pool. GUI descriptor pool. Let's see if that works. Okay. Oh wait, validation error. I is not greater than 0. Ah, yeah, I forgot to. Oops. Fill these out. Cool, those validation errors are gone. All right, now when we're initializing I'm GUI, we can give it the GUI descriptor pool. And let's see if that now initializes successfully. And nope, it does not. So abort has been called image count greater than or equal to min image count. Oh, so there's another one for image count as well? Yeah. Yeah, we'll just set min image count and image count to the same thing. All right, and now we're getting an issue because of the render pass. So now we need a render pass. All right, that is the next topic for the GUI. All Okay, so we'll submit this. Create GUI description for past creation. But now we need to create our render pass. So let's do, we're going to need to split this into separate files pretty soon. Let's do create, we need render passes. Okay, yeah, this is, we'll just create them in here maybe. Pass create info, render pass create. Create info, render pass create. Okay. Okay, so we need attachments, we need dependencies, and we need subpasses. That's what we need here. So I'm going to call this create swap render pass. And then for attachment description, colored attachment. Okay. Flags. Yeah, we need the format. So let's do swap or color format. Samples, sample count 1, MSAA. For the load op, this is whether you want to clear it. We're going to clear it, and then store op. We are going to store it, and then for the stencil, we don't care about that. Initial layout. This is color attachment. And the same for the final layout. So these are our attachments. And then for subpass dependencies, okay, source subpass is subpass external destination is 0. Okay, so for the mask, essentially you just want to make sure that the image is not being written to from the previous pass before the next one. However, I think, yeah, this should pretty much be guaranteed to never happen just because of the way we have things set up, I think. However, we have to make sure that the image layout transition happens at the right time is the main issue, I think. So the source subpass, it's that. And then, so the source stage is the color attachment. So we're starting as color attachment first swap, then we are transitioning to present source. Cool, that looks like it works. Submit that. All right. I think that's gonna do it for tonight. So yeah, I think I'm gonna wrap the stream up there.